Okay, so hi everyone. Last time we saw Shamir's protocol, an interactive proof for TQBF, which is p-space complete. And with that protocol, that concluded the journey of characterizing the power of interactive proofs in terms of, let's say, which languages they can decide in principle. So we learned that IP equals p-space. So what else can we study about interactive proofs? So in some sense, we have built up tools and we have moved farther and farther away from tractable languages where, yeah, the verifier was remained always polynomial time and the prover was doing more and more complex computations to prove more and more complex languages. But those languages, in some sense, are kind of far away from those languages that interest us. And in some sense, we would like to ask, how can interactive proofs help us check computations that an actual prover could run? So this leads to the concept of doubly-efficient interactive proofs. That is the main subject of today's lecture, okay? So to appreciate just how hard the prover was running, so in the honest prover, it was always, in the case of, say, sumcheck for P to the sharp P or Shamir's protocol for TQBF, was always asked to send messages related to some Boolean formula phi, right? You know, whether we are counting a number of satisfying assignments or putting in front a bunch of alternating quantifiers, either way, there was some work associated to this Boolean formula. In the case of the sumcheck protocol, it had to basically construct polynomials obtained as partial sums of the arithmetization of this formula over the Boolean hypercube, okay? So the Boolean hypercube had n variables, or at least had n dimensions when the formula has n variables. And then it had to evaluate that polynomial at each of these points, okay, almost all of those points. So roughly the work was, like, say, on the order of 2 to the n times the size of the formula. And something similar was happening in Shamir's protocol, where in the first polynomial sent in Shamir's protocol was after applying all of these product and coproduct and sometimes reduction operators to construct this, to derive this linear polynomial that is sent in that first message. And that one involves basically aggregating information from a tree of size 2 to the n roughly, where the underlying formula again was evaluated on roughly 2 to the n points, roughly 2 to the n minus 1. And yeah, some of these computations can be done in polynomial space as not just exponential time, but you could potentially not keep around the prior results and somehow kind of tally them with some running sum or running, so you can sort of traverse the tree in some smart way. So you're only using polynomial space, but still that was an exponential amount of time. But you know, that is maybe not surprising because you know these are hard languages. Okay. In fact, in Shamir's protocol is not only 2 to the n, but if you pay attention, because there is n squared rounds, the running time of the honest prover is even 2 to the n squared, okay? And this is true also for Shamir's original protocol, which some of you may have seen in the worksheet today already, or you will soon. But you could say, well, what about computations of interest? Let's say that we are interested in this pretty sort of straightforward, let's call it machine language, that basically says, give me a machine, and I would like to define the language of inputs that are accepted by the machine. And this machine maybe runs in certain time, or certain time t, or in some certain space s. How can these, like if we were to reduce this language to, for example, say TQBF, you know, what parameters would we get in the Boolean formula in terms of t and in terms of s, right? Because this is like a tractable language, right? If you want to decide this language, all you need is time t and space s, okay, whatever those are. So if you go back to the slides that we did not present from last lecture, proving the hardness of TQBF, you will find that if I reduce such a computation to TQBF, we're going to obtain a Boolean formula where the number of variables is on the order, is at least log t times s, okay? And roughly speaking, that's because the way you construct a TQBF to encode a machine computation is basically it's like a search through a configuration space, okay, where kind of you're doubling each time the length of your path inside this kind of a directed graph of connected configurations. Each configuration has a size S because you need to represent the state of the machine. So you need at least S variables, and you have this kind of log T depth to express this size T path. So that's why you have this log T times S. And this means that, let's say if T and S are polynomial, okay, in some input parameter, then it means that when you have 2 to the number of variables, and that number of variables is at least this one, you're going to have a prover that runs in time on the or at least T to the S, which is super polynomial even when T and S are polynomial. Okay, so this is saying, all I'm saying is that whatever techniques we have already, for example, for TQBF, if you just take like a standard polynomial time computation and you reduce to it, which in principle could produce a TQBF instance that is tractable, okay, leads to a prover that is inefficient, okay, which is annoying, right? Because maybe we would want an interactive proof for a tractable language where the prover itself is tractable, okay? So what we've learned is that to the extent that we want to make some progress on interactive proofs with efficient provers, we are not quite there yet. We're going to have to come up with some more ideas, okay? So is the point about this slide clear? We're just trying to basically directly recycle what we have and see if we just kind of scale down the TQBF problem to be something about some tractable, to encode a tractable computation. Maybe the prover would have been tractable. Turns out it's not, okay? All right. I don't see questions, so I presume this is clear.
Why at the end you have n to the omega of 1?
Well, you know, you're going to have generally in a computation, we have a space that is maybe super linear or something like that, right? So T, okay, I'm using n. Now maybe I should fix it in my slides. There are 2 different n's. So there is the n number of variables, and then there is the n, which is the sort of the thing in which T and S are polynomial in. And this first n is the end of the number of variables, and the second n is the other n. Sorry about that. I should, it's another small thing that I should fix in the slides. Let me just take a note. Hopefully that clarifies it. So there's a question by Meet. So the size of the formula will be of size that is polynomial. Well, the machine, we don't care so much about the machine. The machine has constant size, right? It's a Turing machine. It has like some fixed constant size. It could, for all we care, it could be triply exponential in M, and we will be generally fine. But the size of phi will be polynomial in roughly log T and S, okay? So if you take it's not going to be like a big formula. It will be polynomial, okay? The problem is that we have a bad dependence in the number of variables. It's 2 to the number of variables, and so the prover, the honest prover, which experiences work that is exponential in number of variables, will experience inefficient work, okay? All right. Any further questions at this point?
Yeah, I'm a bit confused. So the machine takes 1 input and the Boolean formula takes now n inputs. So how do these inputs relate to each other? How do I split them apart, or what does this mean?
So you can think of the input x as being kind of hard-coded in the formula. So maybe I shouldn't have used x here. Maybe think of z, okay? It's not that x, okay? So the formula here is something that encodes the computation of m on a particular z, okay? And these variables are quantified away by the alternating operators in front, okay? So we're just saying that this Boolean formula, when you think about it as a QBF, its truth or falsehood encodes the correctness of the computation of m on z, Okay, but Z, you can think about it as hard-coded in phi.
Okay.
Yeah, that's another maybe thing that I should clarify in this slide. Thank you. And again, like you can just try to, like if you go in the proof of that TQBF is p-space hard, you can just like trace through what would happen for machine computation, because that's exactly what the proof is like. When you prove that TQBF is p-space hard, what you do is you just take like a machine, you reduce its computation to a TQBF instance, and you observe that if the machine had poly space, then the formula that you obtain has poly size. Therefore, it's a polynomial time reduction. But you can redo the reduction in some parameterized way and keep track of what happens to T and S as separate independent parameters. All right, further questions about the slide. So the whole point of this one is to say, now we want to start caring about also the honest prover. And we don't quite have the right tools to have efficient honest provers yet. So this leads to the notion of doubly efficient interactive proofs, where the double efficiency here denotes the fact that you want the prover and the verifier to be polynomial time. Okay, so we're going to additionally restrict the honest prover to run in some polynomial time. And the first realization is that with this restriction, we can only hope to talk about languages that are efficient in BPP. Okay, so we cannot start talking about efficient, like doubly efficient interactive proofs for CoNP or for NP or like polynomial hierarchy or things like that. We can only talk about doubly efficient interactive proofs for BPP in the best case scenario. Why? Because if a language has a doubly efficient interactive proof, then you also have a BPP algorithm to decide it. It is the algorithm that simply runs the interaction between the honest prover and the honest verifier. When X is in L, we know that the verifier will accept with some high probability. And when X is not an L, we know that no prover will make the verifier accept with high probability, including the honest prover. Okay, so like a BPP algorithm can just run the interaction by itself, and it's just as good. It will kind of be correct with bounded error. Okay, so whatever languages have doubly efficient interactive proofs, they must be inside BPP. So this means that to make the notion of a doubly efficient interactive proof non-trivial, we need to be more precise about what we mean for the verifier to be polynomial time. Otherwise, the verifier could just run the BPP decider, right? So in some sense, what we really mean is that we want the prover to be some polynomial time and the verifier to be, say, better than whatever it could do without the prover. Okay? So it cannot be some arbitrary polynomial time. It has to be some polynomial time cost that is better than without the prover's help, right? Because for a tractable language, the verifier always has the option of saying, you know what, I'm in BPP, I'll just run the BPP decider, right? That's an option that is always available, and there's no prover to help out. We want that, thanks to the prover, the verifier saves computation, okay? So, and this brings to the notion that you can conceptualize a delegation of computation, that the verifier had some computation, let's say, that it wanted to do, it's tractable in time t and space s. Now it engages the services of the prover that will maybe run in time poly t and poly s. You can think about it as some powerful server. And thanks to this interaction, the verifier will be able to get by with maybe less time or less space. Here I don't want to get too precise into what specifically we want, but the idea is you want to get something, okay, beyond the sort of what you could have done by yourself. And you can ask, what languages admit doubly efficient interactive proofs? In the best case, it's BPP, but can we at least get something interesting? Okay. Okay, I just didn't write it here, though. Usually, I view the concept of doubly efficient interactive proof as a sort of something fairly flexible, though in the literature, it is usually interpreted as something very strict, where the time of the verifier is linear or quasi-linear. Okay, so you're not allowed to run in quadratic time, like you need to hit, barely read the input, and that's it. And now you have the gap, right? it could be that without the prover, you might have needed, I don't know, n to the 7 to decide the language, or n squared. Certainly not better than n, because you have to read the input, right? And a reasonably popular definition of doubly efficient interactive proof says that the verifier does not do much more work than barely reading the input. Okay, so quasi-linear in the input size. There's a question about how about honest provers? Will they start with some advice or not? You know, that's a notion somebody can consider. Hasn't really been studied because inside BPP, typically there aren't natural witnesses, but you know, you can consider also provers that have advice. Okay. For the constructions that we'll talk about, there is no, I'm not aware of any natural advice that helps out the prover. All right. So there's a question about, is the typical definition? Yeah, so the typical, well, not just the typical definition, every definition of a doubly efficient interactive proof says that the prover runs in polynomial time. Doesn't matter which polynomial time, right? So just some polynomial time, possibly worse than whatever the verifier needed to define, to check the language by itself, right? So it could be that you have a language that takes n to the 7 to decide for the verifier alone. Maybe for the prover, in order to make the verifier save down to quasi-linear, maybe the prover will need to run in time n to the 10. That's fine, okay? So that's maybe like the overhead of proving. Of course, in the ideal case, you would want the running time of the prover to be as close as possible as just purely like checking the language by yourself, right? Can't expect better than that. All right. So I'm not going to give a formal definition of double efficient interactive proof. What instead we'll do is state a result that is clearly about, I mean, that it clearly is a double efficient interactive proof, and we'll go towards proving it. Okay. So I'll just mention that before we get there, that sort of this paradigm of delegation of computation is exactly one of the two things that probabilistic proofs give you. At a high level, probabilistic proofs are useful either for efficiency or for privacy. Efficiency means that the verifier, by virtue of interacting with the prover, either has to read less communication than by itself, say receiving a big witness, or saves computation. That's like how's about efficiency. Or privacy. So we'll see zero knowledge proofs, I think, in either next lecture or next lecture. And yeah, this delegation of computation is something that is not only of theoretical interest, but it's in fact practical. It's indeed the reason why architectures such as rollups in blockchains are advantageous. So kind of in some sense, you have like some difficult computation, then instead of conducting on a smart contract, you kind of push it outside off-chain, some server does the computation, and then the smart contract only has to check the computation, the verifier's computation rather than the original computation. And that's much cheaper. So that's one place where delegation of computation is used already, in fact, every day. Okay. So the classical result on doubly efficient interactive proofs is about computations that are characterized by so-called bounded depth circuits. Okay, so here's a theorem. Here's a theorem that we're going to partially prove. So you're going to give me a language L that is decidable by a circuit of size S and depth D. Now, we also have this technical condition, log S space uniform. I'll talk about that condition in a moment, but for now, just forget about it. So we have a language L that is kind of decidable by a circuit of size S and depth D. Okay, so that just means that you have your X as input to the circuit and outputs, you know, the final answer, 0, 1, and you have the circuit for the language to decide it. And you should think about this as a kind of wide and shallow circuit. Think about like, some parallel computation. So what this language has a public coin interactive proof with the following efficiency. Well, first, the prover time is polynomial in the size, which means that the prover is efficient, right? Because that was S was the size of the circuit, and now the prover is efficient in that. Okay. Moreover, the verifier time is N plus D polylog S. So in other words, well, first it has to read the input. So there's nothing around that, right? So this part is fine, right? Then, unfortunately, it will have to pay linearly in the depth. So if the depth is huge, well, tough luck for the verifier. That's why I'm saying, just think about sort of wide, shallow computations. But then it will have like an exponential saving in the size of the circuit or the width. Okay, so really, actually, the size S really I should think about it as the width. And in fact, the verifier time we won't even need to have much space. It can even run in small space, though that is it's not so important at this point. Now, if the verifier time is small, the communication complexity can't be too large either. And in fact, it is doesn't even depend on the input size. It is D times polylog S. Okay. So the main point here is that you pay for the depth linearly, but you save exponentially on the width, okay, of the circuit. So, and because of that, since you have some speed up over just purely running the circuit, this is a doubly efficient interactive proof. Now about this condition, so we say that a circuit family is S space uniform if there exists a machine that basically writes out the circuit in space S. And you might wonder, why do we have this technical condition? Well, look, the circuit has to have a description that is shorter than itself in order for the verifier to have any savings, right? Because imagine that, I'm trying to convince you that, I don't know, the circuit C on input X is 0. Okay, you have X and you have to read it, but how are you going to keep the circuit C in your head? How are we going to agree on which statement we're going to prove? If you just think of the circuit C explicitly, by the time you thought about it, you might as well have computed it, right? So we need to have what is called in complexity theory, uniformity. It is a circuit descriptor, right? An algorithm that describes the circuit, okay? And not only you want an algorithm that describes the circuit, but you want to be able to kind of pull out information about the circuit in not too many resources. Otherwise, again, if you have a circuit descriptor that it takes forever to pull out information about the circuit, then again, we're back to square one where the circuit descriptor is not really helpful, okay? And here, and you can imagine various ways to have circuit descriptors. The particular technical notion that is used here is that you have a machine that writes out information about the circuit in small space, okay? So the verifier has a small space circuit descriptor, all right? Okay, also there's a question by Hamoun. For comparison, how long does it take to evaluate the circuit? Well, to evaluate the circuit would be S times D. And again, I'm sorry, I really should maybe not call this size anymore, but call it width. So the benchmark, the trivial benchmark is S times D because you have D layers of size S, right? That one, that one, that one, that one, that one. And so you kind of go down and you're going to cost you without the prover to be S times D. With the prover, you pay D times polylog S. And of course, S is at least N because you need to, in the first layer, you need to read the input. And if you think about it as something not very large. Otherwise, if N is comparable to S, then, you have much smaller savings. So there's a question by me, why do we need to have a machine that describes the circuit? Why not have oracle access to the circuit? Well, we will exactly see a sub-protocol where you say you have savings given that you have oracle access to the circuit. But remember, in the end, the oracle is just like it's not really there, right? In the end, if you want to do delegation or computation, you need to actually, like, nobody's going to give you the circuit, like an oracle for the circuit, right? You can only hope to do delegation computation for problems whose description is smaller than the computation itself. You can imagine settings where you have pre-processing, where maybe you look at the circuit once and you keep around a small description for it, and you can reuse it many times, but we won't talk about this right now. That one is the pre-processing setting. In a pure delegation computation model, you must have a description that is smaller than the computation itself. Otherwise, you can't do anything about it. Here, n is the input size. So n is the size of x, okay? And you can imagine that in the first layer, it's kind of small, and then the circuit does like a big computation on this small input, just not across too many layers. Okay.
Yeah. Can you please say again, like I'm a little bit confused about this description of like in the node. So this machine should produce the entire circuit, or you just have to compute it at like every given node?
So we'll make it more precise later. Also, it won't matter too much because we're going to take a different shortcut. Because we don't have, as I was about to say, this is a difficult theorem to prove in one lecture. It takes about 2 lectures to prove. And so we'll identify only something that, but roughly speaking, basically, it's a machine that rather than writing the whole circuit, you basically ask the machine, could you please tell me whether, I don't know, wires 7, 15, and 8 are connected by an addition gate. And in log S space, or in whatever space, the machine tells you, yes, they're connected, no, they're not connected, okay? So this is something, yeah?
S is the size of the circuit, right? S is the size of the circuit.
Yeah, and actually, I'm also doubling it as the width of the circuit, which I'll fix offline.
Yeah, but sorry, as last question, like if the circuit has size S, oh wait.
So
okay.
This is a big S, and this is a small s. This is not the same S. I should make it a little bit more. I'll change the letter. Sorry about that. That S over here, will be in the definition log S. That's why my handwriting wasn't like good enough to show the difference between big S and small s. There's a question about, does something change if we consider private coin protocols? It's a good question. We don't really have many interesting private coin protocols. But all the constructions, double-efficient interactive proofs that we have are public coin, primarily because they use something samjaki inside, and the samjak is public coin. All right, so the proof of the theorem is quite technical. So for today, we'll see what is typically sort of usually taught, and something known as the bare bones protocol, which is basically achieving the same parameters as above, except that the verifier will have oracle access to certain information about the circuit topology. So we'll kind of factor out the issue of uniformity and just basically provide certain information as oracle to the verifier. And the verifier will basically be efficient given that oracle. And the way you obtain the whole theorem is to say, well, if the circuit has certain uniformity, then here's a bunch of non-trivial reasons why those oracles can actually be implemented with further subroutines and sub-interactive proofs, okay? But kind of the key and the core of the protocol, this bare bones of using samcheck, is what we're gonna see today, all right? So how to basically achieve these parameters given, for any circuit, given the verifier has oracle access to certain information about the circuit, okay? And of course, this information doesn't depend on the input. This is like, sort of input independent circuit information. And the main tools that we'll use is sort of more arithmetization ideas, a bunch of sum checks, and some new ideas that we'll see, okay? And in fact, this bare bones protocol is extremely efficient, and it has been used to construct a kind of efficient cryptographic proofs, precisely in this setting where you actually don't even care that the circuit has a special structure. You kind of pre-process that away using cryptographic tools, okay? We won't get again into cryptography, but whatever we'll see today, it is like it's a core subroutine in efficient cryptography proofs, including in practice. All right, so okay, I'll fix up some of this notation before I post the slides. But given putting that aside, any further questions about what the theorem means or what we're going to try to do today?
So maybe just one quick question. So we said that we have a descriptor is able to like tell us in time and space log s, which is like the gate at some position. But can the prover help in this task maybe? Because you said that this oracle is going to be implemented also with subroutine and some sub interactive proof as well. So
yeah, that's exactly how it's going to go. So in the case of uniform circuits, the way you implement that oracle is you ask help from the prover to basically engage in for each oracle call into a sub-interactive proof to check that the claimed answer by the prover is correct. So like the way the whole protocol is constructed is you first construct the bare bones protocol given this oracle, and then either you have cryptographic methods to get out of this, or if you want to leverage uniformity and not use cryptography, then for each oracle call the verifier is making to the oracle, you ask the prover for the answer, and then there is things we want to talk about, basically in sub-interactive proofs to implement these oracle calls as as interactions with the prover. Okay. Yeah. So to answer Nishan's question, yeah. So like if you have this machine, then you can use the fact that this machine exists in order to design interactive proofs to implement the oracle. Okay. But so
sorry, one clarification. So you said M will be implemented as like an interactive proof, and it will be asking the prover for the evaluations of different points in the circuit. But what will M exactly on the verifier side be used for? Like what will it be able to answer to the verifier? M? Yeah. To define the theorems that they will be engaged about, right? So like look, this is if you have a log space machine, doesn't mean that it will run in time log s, right? You may have a log space machine, but maybe extracting information about it will take more time, okay? But nevertheless, just having the machine in your hand defines the problem. And then you can go to the prover and say, look, could you please help me like solve certain questions about this machine? And then you have interactive proofs about that, okay? So just the fact that you have the machine defines the problem, and you can go to the prover to help you sort of solve those problems. But again, we won't be seeing that. That's like much more technical, and it's going to take an entire lecture on its own. What we'll do is we'll assume that we have this oracle access, okay? Further questions about the slide? All right. So as I kind of already alluded to, we're going to be using this sort of wide, shallow circuits. And specifically, we're going to need the circuits to have like this very regular structure. So we'll only discuss about layered arithmetic circuits. So a layered arithmetic circuit is a circuit where we have a certain number of layers, d+1 layers. You have a bounded fan-in, okay? And it's arranged in sort of layers, each of the same size. So this is the picture. So you have some input layer, which has whatever input size, right? So this one we cannot control, it's just n, right? And then you have a layer of size s, another layer of size s, s, and at some point you have the output, okay? But kind of the bulk of the circuit is this kind of rectangle, which here looks like narrow and tall, but really you should think about it as wide and short, okay? Where each gate's inputs are coming specifically from the previous layer, okay? And that's the same at every layer. And you can only get 2 inputs. And the gates are plus and times. So you have the n inputs, 1 output, and you have s internal values for each of the intermediate layers. So for any given input, I have a question. Yeah.
So in layer 1, there are nodes which do not lead to layer 0. They are actually useless, or what are they good for if they do not contribute to the final computational output?
they keep company to the other gates, and that will make notation easier. Obviously, as you start approaching the output, there's only so many opportunities to influence the output the closer you get, right? Because if you can imagine a cone going back, right, there's only so many gates. Like in this layer, there's only 2 things that can influence it. In this layer, there are 4 things that can influence it. Then there are 8, right? But still, for notational, otherwise the notation will just become a mess. Okay. All right. So if you're given a specific input, let's call it as a function VD, okay, for the input layer, this is going to determine fully some number of, some values for these gates, values for these gates, and values for these gates, all the way up to value for the output gate. Okay, so we have this value functions. Once you give me an input function, which represents n inputs, simply by just following the computation of the circuit, that determines values throughout the circuit. And how are they determined? Well, so now we're going to introduce this kind of circuit description. Like in some sense, the circuit is always, like all circuits kind of will look like this. The way they differ is which inputs are connected to which outputs according to what gates, right? The fact that in this circuit, specifically this gate is connected to this one and that one, as opposed to this one and that one, is determined by something that we call wiring predicates, okay? They are basically predicates that tell you where add and multiplication gates are. So here, for instance, you have an add D gate, add D predicate. This is basically saying, if you give me an integer between 1 and s, that means one of these, and 2 candidate inputs, I'm telling you whether they form a gate. So for example, add D 1, 1, 3 equals 1 here. Why? Because we have a 1 here, and 3, and they're connected in, I don't know, a plus gate, okay? But if I had written add D 1, 1, 2, I would get a 0 because there is no connection here, right? So these are just telling us where the plus and times gates are throughout the circuit, okay? And of course, when you're connecting 2 layers of the same size, then you have s times s times s, right? And over here, really, you should have had, I don't know, 1 times s times s, but I'm kind of shoving that under the carpet. The point is that between every time you have one layer of the circuit, you have this wiring predicates which are describing how does the computation proceed, okay? All right.
Could you also describe the value predicate or value function, this V?
So yeah, so this is, you should just think about it, this is X, okay? So you have n inputs. You can think about it as a function from n to f, right? And by following the circuit computation, you obtain the values for this layer, and then you follow again the computation, you obtain the values for the next layer, and so on and so forth until the end. Okay? So these are input independent. This is just the topology of the circuit. And once you give me the input, I just know how to follow these things to get to the output. Okay? All I'm saying is that this is like, I'm just like giving you notation to describe this thing and its computation. All right? So why are we using all this like super precise notation is because we want to build a protocol for it, and we need to kind of talk about the circuit. Okay. So just remove that one. Right. So the wiring predicates describe the circuit. Okay. So add I and mult I at a certain input ABC will be 1 if the 8th value in layer I minus 1 is addition or multiplication of the bth and cth values in layer I. Okay, so that's kind of what we saw already. Now, the fact that in an arithmetic circuit you have 2 types of gates, plus and times, means that we have 2 types of wiring predicates. Now, it's actually a pain to keep track of these 2 gates, and it actually doesn't really add anything in terms of understanding. So from now onward, we're going to assume that we have just one gate type. Let's just call it G. which maps f squared to f. Doesn't matter what this gate is, okay? And we'll just call WP for wiring predicate 1 through WPD, wiring predicate D, to be the wiring predicates for this one gate type G. This is just to simplify my slides, okay? It will be straightforward to just go back and handle any number of gates. In fact, in the worksheet tomorrow, there is such an exercise to handle any gate set, okay? But it's really straightforward, okay? So from now on, forget about add and mul. We just have one gate type. If you want to feel comfortable, think of like a NAND gate, even though it doesn't really make sense in an arithmetic circuit, but just, think of like, some one gate, okay? But again, NAND here doesn't make sense because it's not a Boolean circuit. You really would need plus and times, but still, we're going to work with one. All right. Okay, this was just to establish notation on layered arithmetic circuits. All right, remember, it is a circuit with fan-in 2. It is arranged in layers of equal size, okay? And it is described by wiring predicates, okay? All right. Any further questions about this slide? What the W's are? Where are the W's? Oh, WP. This is wiring predicate. I'm just using WP1 through WPD as the generic add and mul D for the gate G. Wait, further questions? Okay, we haven't done anything so far. We've just basically said we're going to talk about circuits, and here's notation for it. So in this lecture, this is the first time that we're going to be doing some, I guess, very explicit use of the notion of low degree extension. We briefly mentioned it in the second lecture when we talked about the arithmetization for sharp SAT, that we obtained a polynomial that agrees with the function that extends everywhere, and therefore that was a low degree extension. Here we're going to be doing something a bit more explicit, and so this slide is basically meant to introduce the notion of low degree extension as a standalone thing. We'll be using it a bunch of times in this course and also in Tom's course, okay? And fortunately, you already saw the low degree testing lecture yesterday, which will help to understand this concept, even though there is no testing here. So we're going to be talking about functions defined over a field, usually over a subdomain. So we have some subdomain H over the field, and we have some function defined over it, okay? Now, a polynomial, which of course is defined everywhere on the field because it's a polynomial, is an extension of the function if when you restrict it to the domain of the function, you get the function, okay? So another way to view it is that you have this function is defined on the domain, the polynomial is defined everywhere, and they agree, okay? So it's not just an extension, but it is a low degree extension if f has low degree. Now, low degree changes what does low degree mean changes depending on the setting, okay? But there is a minimum degree that you cannot usually do better than, okay? And the minimal degree is unique, okay? And you can compute it using Lagrange interpolation, okay? So let's kind of look at this expression. So I take my function and I multiply it by something called the Lagrange polynomial at alpha, okay? It's a polynomial that we can actually write explicitly. And this has the property that when you plug in a value x that is equal to alpha, then you get 1, okay? Why? Because let's see here. This is the Lagrange polynomial at alpha. If I plug in x equals alpha, I get alpha minus beta divided by alpha minus beta, that's 1. You take the product over whatever it is, you still get 1, and we're good. If instead you plug in some x that is in H, but not alpha, let's call it alpha prime, here you're going to have alpha prime minus beta, right? Divided by alpha minus beta for every beta that is not equal to alpha. But at some point, beta is going to equal to alpha prime, and the numerator is going to equal to 0, okay? And so this whole product is going to go to 0. So this Lagrange polynomial you can think about it as a delta function on H. It is 0 everywhere except it is 1 precisely at alpha, and otherwise it is 0. Okay? So the way you can construct a low-degree extension P from F is you basically take a linear combination of delta functions so that for any given x on H, you select out exactly the value of alpha the value of F that you want. Okay? And this is just the standard way you interpolate a function into a polynomial. Okay? You have some values you want to hit, you want to pass a polynomial, this is how you do it. This is Lagrange interpolation. Okay? You are likely to have seen this at some point, maybe, I don't know, calculus class maybe, or in high school. This is just the general case. Okay? And what is the degree of a Lagrange polynomial? It is h minus 1, right? Because we have a product of x minus beta for h minus 1 times. And this is typically the minimal degree that you can expect of a low-degree extension. But sometimes for other reasons, you could be working with low-degree extensions that have a slightly higher degree, okay? But the low-degree extension of minimal degree less than h is unique. It is this one, okay? Any questions about this expression, okay? So this is saying, given f, how you compute the unique low-degree extension, though you may have other low-degree extensions with higher degree that you may be working with, okay? And indeed, in the SharpStat lecture, you can go back and check that the low-degree extension we worked there did not have minimal degree. It wasn't a multilinear polynomial. It was some higher degree. But this is how you move from a function to its unique low-degree extension, Lagrange interpolation. Questions? All right. The multivariate case is straightforward. You have some polynomial. It extends a function over a hypercube if it agrees over it. And you've actually seen this picture in the lecture with Tom yesterday. Okay? We have some polynomial defined over the whole f to the n, and it agrees with a function defined over a hypercube. I mean, it is an extension if it agrees with a function over the hypercube. Why do we talk about hypercube rather than funny domains? Because, well, hypercubes are well behaved and funny domains are complicated to talk about. And if you want to construct an extension of a function defined over the hypercube to the whole field, you just basically do this operation for each variable. So you take this kind of sum over all points inside the small hypercube times the multivariate Lagrange polynomial, which is just the product of the univariate polynomials, okay? Because you want to select out the value alpha 1 through alpha n precisely when x1 equals alpha 1, x2 equals alpha 2, x3 equals alpha 3. That's why you take the product of these, okay? And this whole thing will be 1 if and only if all the Lagrange polynomials are 1. The moment one of them is 0, then it cancels out and you don't select out this one, okay? So this polynomial is an extension of this function through this expression, okay? So low-degree extensions will be used many, many times in this kind of summer school, and they're also used all over the place in constructions for holistic proofs. So this is something I highly encourage you to become familiar with. And this is like a standalone slide. It's not about circuits, just about low-degree extensions. And just basically want to be familiar with Lagrange polynomials and their multivariate variants. Any questions about this slide? There's a question by Yotam on the multivariate case. So it's minimal individual degree, okay? Because here, what we're going to have is that each variable xi is going to have individual degree less than h, okay? So this is the minimal, this is the unique polynomial of individual degree less than h that extends this multivariate function. All right, further questions?
Yeah, so the Lagrange interpolation of a set of points does not necessarily give us the polynomial of lowest degree. So, there could be a polynomial which has an even lower degree that fits all our points.
It cannot be, because if you have two such polynomials, they will agree on h points, and then by the polynomial identity lemma, they will agree.
So,
I mean, there will be the same polynomial.
So if we have, say, 5 points on the constant points, all on the same, all points are the same, and we do the Lagrange interpolation, then won't we get a polynomial which goes wibbly through those 5 points, instead that the lowest degree polynomial then would just be the constant line? Or
it just means that the Lagrange polynomials will be the constant polynomials.
Indeed, the Lagrange interpolation would give us then a constant term.
Again, it must, right? Because if there is some other polynomial that is also an extension of degree less than h, then it would agree with this extension on h points, which is greater than its degree, and so they must be the same polynomial.
I see. That's good.
Good question. Further questions? Great. Okay, so now we have logic extensions behind us. What we're going to do is, again, try to say, okay, well, we want to construct a protocol for this layered arithmetic circuit. We want to try to use a sum check. So we're going to try to arithmetize the circuit and find sum check-like things to prove. And hopefully that will get us out. Okay? So that's the plan. So we're going to arithmetize each layer. And we're going to arithmetize it using multivariate logic extensions. So we're going to take a domain H, okay, of size log s, and we're going to set the number of variables to be log s over log h, okay? Why? Because this means that s, we can basically write a bijection between integers in s and h to the m, right? Because let me just write the expression. If you have size of h to the m, that is the same as 2 to the m times log h, which is the same as 2 to the log s over log h times log h, which is s, okay? So if I pick my h and m like this, h to the m is s, okay? And similarly for n, which is the input size, right? So we're going to have this slightly different number of variables for the input layer, okay? And the first thing we're going to do is we're going to rewrite the. Oh, by the way, I didn't say why are we using multivariate extensions? Because our sum check works for multivariate polynomials, right? Like the whole point of using the sum check is that you're peeling off one variable at a time, right? So we're going to want to work with multivariate polynomials. That is why we're here, basically going out on a limb and trying some idea that involves a multivariate logic extension, okay? So our first idea is going to say, okay, we're going to take the circuit and rewrite its computation as summations. So fix z to be some input to the circuit, and the input layer is defined as saying, okay, at input A, that is just ZA, right? And then each subsequent layer, we can actually compute the value anywhere in that layer by considering all possible combinations of the gate, and then we select out the gate that we want according to the wiring predicate, right? Because we're saying, hey, I'm in layer I, I'm wondering at location A, what is the value? And say, well, I don't know. Look at all possible pairs of inputs, B and C, right? And see what the wiring predicate says. It will say 1 for one of them. For that one, you should say the gate, you should evaluate the gate on those inputs from the previous layer, right? So basically, there is a way to progress in the circuit through sums, okay? And of course, because we have this bijection between integers 1 and s, I can write here bc and h to the m, right, as opposed to an s. And again, if we had two types of gates, then this expression would have been, twice the size with a sum in between, okay? And I wouldn't have had space for that. All right. Then what we're going to do is we're going to logically extend each layer. We're going to take we're going to extend the input layer. Previously, we had VD was defined just on H to the M input, right? This is the number of variables for the input. But now it's going to be defined over the whole field. And how do we extend it? We would just extend it with Lagrange polynomials. This hat here, it is often used in the literature to denote an extension of something without the hat, the unique extension. An extension of the ith layer is similar. What we're going to do is we're going to extend this expression, right? So we have this thing, it's evaluated at A, and we're going to have to consider all possible choices of A, like we did here, okay? And we put here the value VI of A, right? So this is VI of A, right? So we have extended. This is a polynomial that extends the values on the ith layer. And crucially, now we have a relation that involves the sums that links the extension to in the ith layer to, we can actually put extensions here as well. Oopsie, I should. Because adding hats here won't change anything because all of these things anyways do the right thing on ABC inside the right domains, okay? So now I have a kind of a relation that relates the extension in the ith layer to the extension of things in the previous layer. Okay, there's a note by, I think, Hila that says, should it be VI minus 1? So we are going from output to input, right? So, or at least when I move forward, I get, we go back to the circuit, we're numbering things so that when we go down, the layer increases. So in the summation, we do expect to go from I to I plus 1. Okay, so.
I'm just a little bit lost here. So you wrote down the layered arithmetic circuit. So it's already arithmetic, but what we really are starting from a Boolean circuit, right? That's the computation. And
the circuit is arithmetic, yes, but what is not arithmetic is its description. The wiring predicates are just some predicates, okay? So the wiring predicates are telling us what and where to compute, but they're not arithmetized. So right now we are trying to arithmetize the wiring predicates. And of course, the values of each layer are just, values in that layer. They have no polynomials there. So we're going to want to try to use the sum check protocol. So just the fact that you have an arithmetic circuit doesn't mean that you have a polynomial. But anyway, there's a different way, of course, to think of an arithmetic circuit, which is itself as a polynomial. But that one will have enormous degree, right? Because suppose that you are going to, I don't know, multiply. A circuit of depth D may have degree that is exponential in D, and we may not be able to handle that, right? So we're not taking the circuit and viewing it as a polynomial. Instead, we're slicing it up and we're expressing its computation layer by layer itself as summations that we can, about polynomials, that we can then use the sum check for, right? We're trying to do two things. The main thing we're trying to do here is to use the one hammer we have, which is a sum check protocol, okay? So, and it's really not clear at this point, but if you study the whole literature, the sum check hammer gets bigger and bigger in the sense that it is used in way too many places. It is the one thing that lets us construct probabilistic proofs. There's a few other things, but not many others, okay? So in some sense, our only chance is to reduce to a sum check problem and apply the sum check protocol, right? To do that, we need to have polynomials of multiple variables that have low degree and summations. So we're just trying to massage our problem to have that form, okay? All right. So the point now is that by writing the progress of the circuit as summations of one layer based on the previous one, then we can extend. So this creates the summations, but not the polynomials. To create the polynomials, we just extend things. And you say, okay, I've extended everything. Okay. And because the summations are over the domain of the original function, then it's okay to put the extensions inside as well, right? It doesn't change. Now, there's one last thing that we need to do, which is if we have our plan to run a sum check on these variables, there is one last problem here, is that this a appears as a parameter rather than as a variable of a low-degree polynomial. Okay, so that's not quite a dependence, a low-degree dependence. Okay, but that's easily fixed because we can just swap out the Lagrange polynomial, or rather not swap it out, but there's the Lagrange polynomial. We can actually express it in some low-degree way by basically saying, look, if you wanted to compare x and a, then I have a bivariate polynomial that compares x and a, where x and a are both variables of a polynomial. And how do I construct it? This way. Basically, I'm just kind of re-arithmetizing the Lagrange polynomial across its domain. Okay. It's not very important right now. It's just basically ensuring that the dependence on a is low degree, because we're going to want to run a sum check on all these variables. Okay. So this term here is basically an equality polynomial. It compares x and y over h to the m, where x and y are both inputs to the polynomial. All right. Yeah. So you can think about it. This is like a bespoke extension of this function. Okay. Just like some nifty, clever expression for it. With this done, essentially we are halfway done, in the sense that we have a sum check problem that relates one layer to the next. So there's a question by Amit, why is it not low-degree as is? Because, well, let's see where a appears. This a in the low-degree extension slide will appear, for example, here, right? Because this alpha appears here, right? So that is not a low-degree dependence, it's just a parameter, right? So you cannot put a variable there, right? So it is not low-degree in the sense it's just a parameter, it's not a variable. So you really need to do something there. It's not just already as is low-degree. All right, good question. All right, so, and now we can just basically think of iterated sum checks. The original claim that the circuit on input z produces, I don't know, some output y, we can just rewrite it as basically saying the low-degree extension of the, of the input function at 0, 0 being the first, let's say we are 0 indexed and I put at 0 the first location, is y. Equivalently, if I open up v0 hat in terms of its sum, this is the claim that we want to prove. We are proving that this sum that involves v1 hat and the wiring predicate for the first layer equals y. Okay? I'm just rewriting v0 hat at 0 using the expression from the previous slide. That's just a sum. That's a sum check claim. Okay, well, we can do a sum check on variables a, b, and c. And this involves 3m rounds, right? Because we are running over this sort of h to the 3m. It will have a soundness adder that we can control, order of mh. The individual degrees are order of h because these are kind of all our extensions of individual degree h. So, so roughly, this is going to be, because m is not too large, it's going to be polynomial in h over f per round. Okay, the soundness adder, something we can control if f is large enough. The honest prover is going to have to think about hypercubes of size h to the m. Okay, but h to the m, now we scaled it down to something that has polynomial size. So it will actually be polynomial size for the honest prover to run the sum check. This is a sum check over a hypercube that is pretty small. Okay. But crucially, the verifier will only pay in poly m and h. And because we picked h and m so that neither of them is large, this is going to be polylog s. Okay. Provided the verifier has the ability to query the logic extension of the first layer wiring predicate at a random point. And right now, this is the information we're assuming the verifier has Oracle access to. So the verifier is given Oracle access to loading extensions of the wiring predicates. That is the information that we're giving to the verifier. Okay. Why does it need to do it? Because when you reach the end of sum check, you need to evaluate the addend at a random point, right? But then you also need to query v1 hat and v1 hat. So v1 hat at some random point and v1 hat at some other random point, right? Like that's what happens at the end of the sum check protocol. So the prover could just say, hey, look, I'm just going to tell you what is the answer to v1 hat at a random point, let's call it S, and v1 hat at some other random point T. It is gamma and delta. So now the verifier can just evaluate that expression, check it for the first sum check, and now it has the two new subclaims because v1 hat and v2 hat, so v1 hat and at S and v1 hat at T, themselves, they are summations in terms of v2 hat, right? So now you have two new sum check claims. And we have made progress, all right? All right, so we made progress, but we're still not out of danger. What happens if we continue?
So wouldn't this become now exponentially
right? So
big?
Right. If in every layer we double the number of sum check claims, pretty soon we're going to have too many of them. Okay. So now we're going to have to do something about reducing the number of claims. Okay. But at least we've made one step. Okay. And in this one step, the prover was efficient and the verifier didn't really have to do much. It was basically kind of polylog S work, given that it has Oracle access to information about the circuit. And that's it, right? Because the two subclaims is the problem of the continuation of the protocol. So there's a question about how do we define H? H is any subset. H is any subset of F of size, say, for example, log S. Okay. We cannot afford for H to be too large. Okay. Let's say it's at most size log S. It's okay if it's a little bit smaller as well. It can be smaller as well.
So the point at which we need the verifier needs to be able to evaluate v1 hat and at these two random points is in the original sum check protocol. At the end, we query the original polynomial, right? So
yes. And so at this point, the prover just tells the answer to the verifier so that the sum check can conclude, assuming that those answers are correct. But then this gives rise to two new subclaims about those claimed values by the prover. This one and the other one down here, right? So basically you can imagine that the first sum check has concluded once the prover provides those answers. But now we're left, I mean, we're not done, right? Like we don't know whether the prover lied or not. So now we have these two new subclaims about v1 hat and the other v1 hat, but we can each of them open up into their own sum. Okay. Wait, like this seems like a complicated protocol, but it is among the fastest things that are implemented in practice. It's like it's very efficient. So what is S and T? These are just this is randomness from the sum check. Okay. This is from the sum check. At the end of the sum check protocol, the variables A, B, and C will need to be evaluated, will be fixed to random values chosen by the verifier through the sum check protocol. And the verifier will be tasked to evaluate the addend at those random points. Okay. And in particular, B will be some S and C will be some T. And then that will kind of be what the verifier needs to do. All right, Emanuele has a suggestion. Why don't we take a random linear combination of these two? And that's exactly what we're going to do. So that's the next slide. So avoiding the claim blowup, so we had this one claim about layer 0. We're going to run the sum check, right? Here's a pictorial thing of how it looks like. And now we have these two claims. But what we can do is that the verifier can just say, here are two random points, alpha and beta. Why don't we talk about a random linear combination of these two claims? And magically, this is really like out of luck, if you take a random linear combination, it's like the part about v2 hat factors out, appears only once. Okay? So if either of these claims is not true with high probability, then this new claim is also not true. Okay, just by linearity. And now we just have a slightly more complicated kind of expression to claim, to prove, but that's fine because all this stuff the verifier can evaluate by itself, okay, efficiently. And so it's just twice the effort of evaluating one of them, so who cares, okay? And the next time when we do a sum check, we're gonna be back to two claims of this sort because we're gonna have two claims about v2 hat, right? Here they are, one and the other, but these two look exactly like these, and we can again take a random linear combination, and this is sustainable, okay? So we're gonna alternate a sum check and a 2-to-1 reduction. Sum check, 2-to-1 reduction, sum check, 2-to-1 reduction, okay? And kind of the common claim will always look like this, okay, for a sum check. In some sense, the beginning claim is because there wasn't a 2-to-1 reduction before it, then it doesn't have this extra structure, but all other claims will look like this, okay? And so here how it is, we're basically, this is like a daisy chain of sum checks, so interleaved with 2-to-1 reductions. Any questions about this? Now here, like I'm using pictorially a bit more, you see the S and T that was used here, right? This is the randomness from the verifier side. Here I'm showing the oracles that the verifier in principle would need to access to evaluate the addend. This one is kind of dotted because the prover will provide the answers and the verifier will kind of give them to the sum check verifier instead of actually querying v1 hat, right? And those answers lead to these two subclaims, okay? And of course, with each layer, the verifier is going to query the corresponding wiring predicate at some random point, okay? So overall, there's going to be that each wiring predicate, it is queried exactly once at a random point, okay? Or more precisely, the logic extension of each predicate, okay? It's possible to push such 2-to-1 reductions to optimize the sum check protocol as well. Not quite sure, Amit, maybe you can use voice, or I'm not quite sure I understand the question.
Yeah, so in the sum check protocol, there are a number of claims that we prove in a round by round fashion, right?
Yeah.
So I was thinking that here, like we did reduce the number of claims from 2 to 1. Is it also possible to reduce the number of rounds in the sum check protocol by reducing the number of claims?
So it's a good question, but the situation is different because those are not parallel claims. It's just when you do the previous round, then you obtain the new claim. So you cannot have the new claim before you've done the round, okay? Whereas here, these are parallel claims. These are like one claim, another claim, and we're reducing them, okay? They're not like in sequence. In the sum check protocol, instead, the claim that arises at each round precisely came out because you did the previous round's reduction, okay? So the situation is different.
Okay. Yeah.
The question by Hamoun about why can't the prover cheat? Well, I think it should be rather, I mean, it's just by linearity, right? So you have an equation, another equation, right? So if either of them doesn't hold, then with high probability over alpha and beta, then this equation cannot hold. It's not about the prover, it's just like probability, okay? And then because of the structure of the equation, I can move the alpha and beta in a convenient place so that I have a new expression that does not involve two copies of these two v2 hats. I only have one copy. Okay. Good question.
I have a question. So
yeah.
Why is there an arrow going from the sum check box to the v1 hat box?
You mean here?
Yes.
Well, because remember at the end of the sum check protocol, the verifier wants to query the addend at a random point. Now, this part the verifier can evaluate by itself. This part requires querying this one, so here it is, and querying these guys so that then it can evaluate G and get the whole product, right? So here I put that the sum check verifier would like to query v1 hat at S and T. But then, because the verifier doesn't really have v1 hat, instead, as an answer, it provides what the prover gives. Okay. All right, hopefully that gives an answer. All right, so we're basically done, and we're just going to summarize in the next slide. But any further questions about this?
Alessandro, can you please just like I feel that I kind of lost it. Like, how do we like when we were going from generally overfilled to this low degree extension, like I just sort of. So the idea is this. So we have this Boolean formula defined by this circuit. Then we reinterpret it just as a polynomials over field, like over F, right? But then we do something strange. Kind of we say that every value is a bunch of values.
So not quite. We are. Let me go back there. It's really inconvenient, not convenient that Keynote does not have go back animations. Right. So here, okay. Hopefully everybody feels comfortable with the fact that we are expressing each value as a summation over the previous layer. Hopefully that makes sense, right? Because we're just considering all possibilities and select out what we want. Now, if SumCheck didn't care about polynomials, maybe we would be done here, right? But in order for us to run SumCheck on anything, we need to be able to have polynomials in the addend. And these are not polynomials. This is a function, okay? And it's also a function of B, and a function, like it's just a function, right? It's a function from h to the m to f. That's not a polynomial, okay? So this whole thing is just like not something we can talk about. So instead, what we're going to do is we're going to extend everything that we see.
No, but I mean, it was polynomial before we reinterpreted B as a vector in HM, right? So if we say that B is just in F, which it initially is. Oh, wait a second.
No, V is not. V is just is the cross section of values on a. Well, let me say two things. Let me go back to the circuit. Now, V was just a cross section of values here, right? Now, because this is an arithmetic circuit, you could, in some sense, say, okay, look, where does this guy come from? Well, it comes from a plus of these two things, which comes from the times of those two things, and the plus of those two things. So each of those things is a polynomial in the input, ultimately, but it may be a high-degree polynomial, and we won't be able to handle it.
Yeah.
Okay? Because, look, if you have a degree D, sorry, if you have a depth D circuit, you could have degree up to 2 to the D, right?
Yeah.
Which is very high degree.
Yes.
So we cannot afford that. So we're just going to forget, like we are not going to use at all the fact that this thing is a polynomial by itself. Instead, we're just going to kind of syntactically see this whole layer as a function and then extend it.
Okay.
And because we are kind of extending it ourselves, we have control over the degree.
All right. Oh, okay. Thank you.
It's a clever protocol. All right. So I want to go to the last slide and kind of summarize, and I'll take questions. Okay. All right. So this is kind of a diagrammatic summary of the protocol. We start out with one claim about the logic extension of the output. We apply a SumCheck that causes one query to the wiring predicate to the first layer, to the output layer. That causes two claims. Then we take a linear combination. We're back to one claim about V1 hat. And again, you run a SumCheck with one query to the wiring predicate for the second layer. This gives two claims, combination, and we continue. At some point, we have one claim about the input, which the verifier can compute by itself. Okay, because this is like a quasi-linear in the input size. So, and yeah, we did not really discuss that the input, how to handle the input layer. This is semi-technical, not too complicated. Just gonna go over it. Just believe me that once you get to the input, you can just compute its logic extension at a random point in something basically proportional to the input. Okay. So a couple of points. First, the whole thing is public coin because the SumCheck is public coin and the linear combination was just to random values. So the whole thing is public key. The number of rounds is D times the sum check on something called, sum check on 3m variables plus the random linear combination. Now the sum check on 3m variables is going to have 3m rounds. Okay, so overall, the number of rounds is D times m. Okay, and if you remember, m was log s over log h, and h is log s. So this would be D times log s over log s, which is at most log s. Okay, so it's D log s rounds. The combination complexity is D times whatever the sum check does on 3m variables with individual degree, order of h plus 2, where the plus 2 is because of the gate. But okay, so if you have 3m variables and this individual degree, that means the communication complexity of a sum check is m times h. So we have D times f times h, and that is D times polylog s. And everywhere here is big S, yes. The soundness error is we're doing D things in a row, right? The soundness error of linear combinations is 1 over f, and the soundness error of the sum check is going to be n times h over f. So overall, we have D times h over f. It means that f, as long as it is of size D polylog s, we're going to be fine, which is not large. The prover time is D times sum check, but the sum check is polynomial in h to the m, which is s. So it's D times s, or poly s, which is still poly s anyways. Okay? And again, I should be more precise. This is maybe poly D and s if I think of them as independent parameters. Finally, and perhaps most importantly, the verifier time is D times poly mh, which is D times polylog s. So overall, the verifier has saved time given all these queries, of course, right? And these evaluations is something that we're not discussing in this in this course, and I mean, not only in this lecture, but in this course, how it can be done, and it's actually rather technical and sometimes tedious to implement these. Though, interestingly enough, usually in practice, this other part is not really used. Usually it's the bare bones protocol on its own that is used in practice. Or sometimes what happens is you have highly structured circuits, and then people have kind of come up with like tailored sub-protocols for the wiring predicates of tailored circuits, maybe circuits for, say, fast Fourier transforms, or circuits for matrix multiplication. And then you can, those are kind of extremely structured, and you can just basically directly write down the logic extension of the wiring predicates. Okay. And I think this is a good time to sum up. So what we've seen today is a construction of a doubly efficient interactive proof. This is not the only construction of doubly efficient interactive proofs. There are other constructions out there. They're all pretty technical, more than these, usually. And many of them use the soundcheck protocol somewhere. But the whole point is to consider tractable languages and try to make the verifier run faster than just running computation by itself. Okay, possibly with some overhead from the prover. But as long as the prover runs in polynomial time, then we're fine. Okay, so I'm going to stop the recording and take on more questions.